Welcome everyone to our QWebinar. This is our second QWebinar. In the first QWebinar, one of our board member, Pavel Gora, gave a talk about introduction to quantum computing. And in this QWebinar, we will have a guest. He will be our first guest. Also, this will be our first experience for webinar for me and Zoltan. So we are apologizing for any inconvenience in advance. So it will be also experience for us. I mean, we are also learning. So today I and Zoltan will be the moderators, and the organizers, me and also Agnieszka. We are all QWorld members. I will also shortly introduce QWorld. Maybe some of you heard for the first time, and then Nathan will be on the stage. Zoltan is from Hungary. He is also in the group of we called Q Hungary, and I am in the group of Q Latvia. Agnieszka is also in Q Latvia. This is our agenda. I will shortly define our protocol, just a simple few rules. Then I will make a short introduction of QWorld. Then Nathan will take the stage, and then we will have a question answer for the Nathan. And then basically the webinar will finish, but if some people are interested in QWorld, and maybe we can unmute also the people and we can just try to answer your questions and try to introduce more details. We are quite careful about ethical rules, and then so our activities are dedicated to providing harassment-free experience. We don't expect any incidents, but just in case, if you want to report anything, immediately contact me or Zoltan. So please don't record or broadcast this meeting because you didn't ask any permission from the other people. But we are recording this, and our recording video will be available in our YouTube channel, and each applicant will be informed with this link. We will send an email that you enter in our forms. And to be smoothly operating, let's say, webinar, please communicate with us in the comment box. I and Zoltan will check it regularly. You can also ask your questions there, and then we will just ask them to Nathan, most probably at the end. So this is our motto or slogan. The idea of QWorld is just invite everyone, because this second quantum revolution is happening, and then we just facilitate or some intermediate people and just invite everyone. So this is our beginning story. And who we are basically a network of groups and individuals, and we are collaborating on education of quantum technologies or implementation of quantum technologies. And so what we are doing, basically we are popularizing especially quantum software and quantum technologies, and we try to involve more people to the field. And we are organizing many public events, and we are also doing some academic events, and we have many local groups. They are working locally. Also, we are working internationally. We have a very simple goal. So is there some important in the chat? Okay, just hey, hi, okay. So our aim is very simple. In 5 years, so everybody is trying to, of course, contribute and build the open access global ecosystem for quantum technologies. Nathan is also one of such person. And just in 5 years, we want to create an environment, let's say, or enough material and enough experience in a way that then any interested people or group all around the world can easily just be part of this ecosystem. So we have such goal of for 5 years. Basically, everything starts with an international project. We call it QDrive. So there was no pandemic, etc. last year, and we just enjoy this summer. And it started with a small group in Latvia. I was lead this group. Then we just jump on a car and travel more than 10,000 kilometers. As you see here, and we organized 2 or 3 days long 11 workshops in 8 different countries. So we hand out more than 200 diplomas, and here is also a picture from one of these events. This was exactly in Budapest, and if you check closely the photo, you can find me there. Zoltan is there also. Yeah, and the idea of QWorld and the things under QWorld basically matured during this QDrive trip also. So it wasn't only some educational activity, also it's really give us some inspiration, and then we just built this initiative. So under QWorld there are different groups. The main groups are Q cousins, we call it, to each other, Q cousins, and here you see 6 Q cousins. These 5 of them entangled during this QDrive, and then Q Russia joined us in November in 2019. And nowadays, India, a group in India and also in Slovakia, they are joining us, and we are just talking with some other people globally. So idea is just have a network. In the same network, we can support and encourage each other. So this is the main group. Also, we are, let's say, we have a kitchen. So if we need some material, we should cook it. We call it why it's a kitchen. So to do some events, let's say to organize some workshops or to design some courses, we definitely need some educational materials. And this is our project of QKitchen, and we have a GitLab repo for this. And we are also like collaborating to develop new materials by using this QKitchen. So we also promote equality, diversity, and inclusion. This is why we have also a separate channel, or let's say working group. It's called QWomen. Our idea is to involve more women and underrepresented groups. This is relatively new compared to Q cousins. Under this QWomen channel, we have a group. It's called Q sisters. At the moment, we have 2 groups from Turkey. One is QWomen in Istanbul, and the other is QWomen Ankara. And yeah, we also expect to grow in this part. So we call juniors, not like at the university level juniors. For us, juniors are high school, because high school students can already start to learn quantum programming and some basics. So we also have a separate channel for this. So basically quantum juniors for, let's say, quantum future. I mean, everything is started nowadays. If we just attract some high school students nowadays, I mean, when this field become more and more mature, these students will be more than ready. I mean, in 4 or 5 years, when they are graduating from their bachelor degree, yeah, they will be almost more than ready. So a short summary: in our network with different groups, we organized more than 30 events in 18 cities and 13 different countries, and we hand out more than 600 diplomas. And our workshops is not like this 1 hour or half-day workshops. They are really 2 or 3 days long workshops, and we did more than 30. Recently, QTurkey also implemented one online workshop, and QTurkey also implemented one 2-day long hackathon. So this is our short introductory. I will stop now sharing. So I will give a stage now, Nathan, and then if you have some questions about QWorld, after Nathan's question and answer session, we can talk in a more informal way. I would like to thank a lot for Nathan to accept our invitation. He is kind of our first privileged speaker, and I guess the topic is also quite parallel to our aims. And he's, I think he's a physicist, already a researcher. He's a contributor for open source, let's say, science. And he also getting some administrative job as well under Unitary Fund. I guess, yeah, it's also one of the, let's say, great ideas to really build this open access, yeah, quantum system. So Nathan, are you ready?
Yes, thank you, Abu. Can you hear me well?
Yes.
Yes. Thank you, Abu, and thank you all. And so let me share my screen and start the presentation. Do you see the screen well?
Yes, yes. Thank you.
Okay, great. So yeah, I would like to thank you, Abu, Zolt, and everyone involved in the QWorld organization of this first QWebinar, and all of you that are connected or may watch the talk later on. And I think it's very nice, all the kind of work that you're doing right now remotely, but towards inclusiveness in quantum science research. So I will speak about my personal story as it was requested by the organizers, which starts with research, then I got involved into the development and management of a software package that was already existing, the Quantum Toolbox in Python, and now my journey at Unitary Fund, where I really get the opportunity to help many more projects, students, and researchers. I would like to thank everyone who already sent some questions, and I will answer to these questions. I will also ask Abu about probably sharing the written questions and my replies. And so I already tried to address some of them in the presentation. So yes, this is a personal story. So we start with my research path, how I got into open source development. First, I was just a user of QuTiP, and then I will speak a bit about Unitary Fund and in general quantum technology and open source, how the two things are going together. So I'm a physicist. I studied at the University of Milan, although I also performed visits at Copenhagen University and Imperial College London through Erasmus programs that I'm really proud I could benefit of them. And then I did my PhD in Southampton with Simone De Liberato, working on solid state quantum electrodynamics. I then moved to Japan for 4 years. RIKEN is a Japan National Lab, and I worked in Franco Norris Group, where really this software package QuTiP has been really hosted for a long time, and actually it was born there, and it's really looked after by a wide community, but mainly at that research group. And more recently, I also joined the Unitary Fund with Will Zhang and other researchers, Andrea Mari and Ryan LaRose and other collaborators, and we'll speak a bit about that. And I also wanted to mention that I write a monthly newsletter about quantum technology, and I'm involved also in communities of researchers, such as the Association of Researchers in Japan, and I also have provided in the past some insight on the technology transfer in quantum tech through a consulting hub that is still active, Quantica. So talking about my research, I think that a common path to try to describe it is that I study cooperative phenomena in many-body quantum physics. So these sketches try to represent what would be two-level systems and electrons. If you're not familiar with them, it's just a pictorial representation. And I've studied this kind of effects in several systems, from collective electronic excitations in stuff such as quantum wells or microgravity, to superconducting circuits where one can engineer specific properties of these so-called artificial atoms that are not present in nature, to other systems that could be modeling qubits or spins, or again two-level system, which is just a way in which physicists usually refer to atoms or more complex structures. And a common thread in my research, I would say, has been like trying to get more out of the sum of single, constituents in matter, but also try to leverage cooperative behavior in scientific research, which now I think really occurs in open source development, sometimes more than in the general academic setting, unfortunately, I would say. And this is not no one's fault, but is a series of circumstances where in open source software, you really see a lot of excited people about what we're doing. And I think because the nature of the work there is inherently collaborative. A bit more about my research, because as a personal path, I would like to stress that I started during my PhD by studying light matter interaction in these artificial atoms and structures. So here you see that it is possible on the left to observe sunlight emission at different frequencies. These frequencies are tunable in intensity and in frequency. And this is also due to the fact that in these artificial atoms, one of those sketches is on the further right, it is possible to tailor the rate of emission, this so-called Fermi-Golden rule, and also the shape of these wave functions that represent the state of the system, which you see in the central figure. And some of the applications relate to terahertz technology. So electromagnetic waves go to very high frequencies to very low frequencies. And there is something called like a technology gap, which is this terahertz range, which goes to around 10 to the 11 to 10 to the 13 hertz, in which we really don't have a really compact and reliable detectors and emitters. In airports now, you're seeing these body scans, but these are only appeared in the past 10 to 15 years. And these are quite bulky things. Or another place where you can have terahertz emission, it's in an accelerator, but these are huge labs. So actually, there is a lot of research to try to obtain terahertz emission and detectors in compact, sort of like monolithic optoelectronic devices. And this has been a focus of my research. And let me also mention that terahertz technology has applications that are very interesting for defense, security, and also for senseless and contactless medical imaging, because a series of molecules, including, for example, molecules that can be generated by explosives, have resonances and they vibrate strongly with these frequencies. As I sketched, I'm interested in the collective and cooperative mechanisms that occur in these systems. So this is a sketch showing an atom inside what is called a cavity, which is basically like some sort of setup. Could be two mirrors in which light between two mirrors bounces back and forth. And so this already tells you that it is possible to try to increase the interaction between light and matter in such settings. And this is a very broad field of study in physics, which is called cavity quantum electrodynamics. And I'm particularly interested in when many emitters or absorbers, they're the same, such as atoms, are contained in such devices or laboratories experiments. And so here, let me put some math. I don't want to scare those who are not familiar with it. It's not so important. The expert will get to understand some of the physics in these slides. What I want to mention is this is just a representation of what happens to the more famous Schrödinger equation when one takes into account this kind of noise. And what happens, the most important thing is the bottom row, is that when no noise is affecting the system, the dimension in computational space where these objects live, it's exponentially growing. When we add some sort of noise, this is even worse, because this grows like not 2 to the n, but 4 to the n, so really exponentially fast, even by making very rough approximations about the kind of noise that is affecting the system. And so this is kind of a sketch showing that it's really hard to simulate quantum bits of information or quantum physical systems, even beyond a few tenths of systems, because this becomes numerically unfeasible, because the dimensional space that is required to store this information in classical computers becomes very big. So one thing that I addressed with collaborators was how to study specific sorts of dynamics. And again, this slide is a bit mysterious for non-experts, but dynamics in which specific symmetries occurs, and this sort of noisy so-called Lindblad dynamics includes collective but also local sources of noise. And when these kind of like symmetries that are sketched by this graph on the right are present, such that each constituent of each qubit is, let's say, talking or interacting with each qubit, which each other qubit non-linearly, but with the same interaction strength, it is really possible to cut down the computational space. And so this is an example in which you see that this space on the right is extended, on the left, sorry, it's extended. It can be represented on a block diagonal density matrix, and the space size really does not grow anymore exponentially, but only polynomially. And so there are constraints to these. We were not the first to really understand this. There were several papers doing it, but what I did with Shahnaz Ahmed and collaborators was really to turn this into a software package. And so this is just some, let's say, color maps that show states evolving in this representation of collective states, so-called Dickey states. It's not important to get all of the details, but let's say that the basic idea here is that different quadrants, so different squares, are connected by these dynamics. And this is usually not taken into account when one considers other types of noise that are very hard to simulate. And another part of my research has not only been involved with describing noise, such as the excitations of qubits by the emission of a photon or absorption of a photon, or dephasing as it occurs in qubits, but also systems in which, as you can see here, there is a cavity QED setup, and in which, as you see, there are these sorts of spheres that could be electrons that hop inside a cavity QED setup and hop out. So there is a sort of electrical current going through this system. So this is another sort of way of opening the system, because the system is open in the sense that there is stuff going out, in and out. This can be information, this can be energy, and in this case, it's even particles. And this sort of setups can now be manufactured. This kind of experiments with, for example, gallium arsenide or silicon quantum dots, as it is shown in these lithographs. And what we studied with collaborators were really what was happening when many such electrons go through these cavity QED systems, and the kind of modifications that occur in the way light interacts with matter, and the possibility of having some sort of enhanced cooperative effect in the light emission of these devices. And this can be like really studied in many systems. So for this, I would like to acknowledge my collaborators on these works. And so, as I was mentioning before, we turned that model and that software package really into a full-fledged open source library that then became, which is called PIX, the Permutation Invariant Quantum Solver, which allows to address a lot of problems that are of interest to modern out of equilibrium quantum physics. And since we're using some of the basic features of the quantum toolbox in Python, this already existing project, which is very popular among quantum opticians, Shammah and I then turned it into one of its modules. So now you can import the QTIP.PIQS module into QTIP. And so once again, this is just a way in which, for example, the quantum toolbox in Python, it is now possible to study many-body quantum systems. And I would like to say that the quantum toolbox in Python is supported by many entities, research agencies, non-profit organizations, and research groups that devolve time over students or research associates to work on the project. And talking about the QTIP, let me mention that this is really a quantum physics simulator. So it is possible to study these cavity quantum electrodynamics, specific instances in which, for example, the vibrations represent some of these bosonic excitations. This is called optomechanics. Also, it is possible to study quantum information processing. So you see on the upper right a block sphere in which this arrow is actually processing around a given direction. And then all sorts of more specific tasks, such as quantum optimal control, which is a theory, which is a subset of optimal control theory, in which basically there is a target, there is a feedback, and it is possible to adjust and enhance the performance of quantum algorithms or quantum protocols, taking into account the fact that there is noise in our system. So this is the same occurs in stochastic dynamics that allows to simulate very refined and subtle differences in the kinds of noise. So this is really something that QTIP is good at doing. And right now there is this emergent NISQ era, noisy intermediate scale quantum computing devices. Basically, it's just the understanding that it is unavoidable even at the conceptual level to not describe noise, even when there are quantum computing processes in place. And so QTIP is a more general framework in which quantum physics can be described, and since quantum physics at its core, it's quantum mechanical, and it also, and information at its core is represented or encoded on quantum, on physical objects that are abide to quantum laws, but this also affects quantum information processing and quantum computing that try to really exploit some features that are intrinsic of quantum instead of classical systems for information processing. So these are just some examples of some of the most famous features and most used features of QTIP that is used for research, education, and also in the quantum tech industry. So you see here a noisy dynamics that is occurring on a block sphere among these two poles, 0 and 1. And then, so basically this sort of dynamics can be described in QTIP in a variety of ways. So it really depends on the kinds of assumptions that you make on the dynamics. So this is a slide more for experts, but let me just mention that there is a very flexible ways in which you can describe time evolution in QTIP. It goes from Lindblad master equations to Monte Carlo quantum trajectory methods to some sorts of coherently and continuously pumped systems known as Floquet theory, in which you try to represent the dynamics on some quasi-eigenvectors, to systems that can both include stochastic effects at the master equation or wave function level, such as SSE solve or SME solve, and also like non-Markovian effects, such as in the Bloch-Redfield master equation or in the hierarchy equation of motion dynamics. So I would like to acknowledge the fact that QuTiP was a project that started and mainly developed by Rob Johansson and Paul Nation when they were in Frank Honori's group at Riken. Frank Honori also hosted and harbored this project for a long time, and many of the lead developers and passive developers interacted with its group. But I would like also to mention Arne Grimsø and Chris Grenay. As it often happens with these open source projects, it was really heavily inspired by the Quantum Toolbox in MATLAB, which is an open source plugin on a closed source piece of software. And over the years, it was, I think, a really incredible intuition to code it in Python, which was not as popular as it is now. And it has become a very robust project, thanks to the really amazing and outstanding scientific tools present in the Python ecosystem. And so one should also mention that this software is free, but if you use it for research, for example, please do acknowledge it in citing the papers that are relative to QuTiP. There are 2 papers that are cited there on the top. It also, if it is used as a software, it has a license connected to it, which is fairly permissive. And then it is developed really using the best tools in software development, such as being compliant to some, let's say, rules that are chosen among developers, from testing to documentation to really the way the code is written and the project collaborates. And now let me also acknowledge the other lead developers, as well as Franco, which is a project manager for the project. So Shahnawaz Ahmed was also specialist in quantum machine learning and non-Markovian bus. Alex Pitchford, who really works with quantum optimal control. Eric Guerre, who optimizes all sorts of code. Boxy Lee, who is revamping the quantum circuit module. And Neil Lambert, who also works on theory of measurement and Markovian dynamics and stochastic dynamics. So these are some of the lead developers, but there is a much wider group of contributors that you can see here, which is just a representative. But you see here is actually a slide I reuse. It says 44 contributors. It was just last year. Now we have 70 contributors. So there is many contributors to the projects, and I really would like to acknowledge these, as well as a lot of professors and researchers that help maintain the QuTiP forum on Google that is accessible to all, where people can post not only bugs, but even questions and answers. And if you're interested into checking out the project, you can look for a repository on GitHub under my account. If you manage to spell my name, Nathan Shammah, there is a repository called Interactive Notebooks. And if you click on Launch Binder, and this is one of the amazing tools from the Python community, it is possible to start tinkering in an interactive environment that runs in your browser without requiring installing anything. And I really would like to thank Marcello Dal Monte at ICTP and CISA to allowing me to take some time to develop these features, as well as the quantum optics notebooks. So here are some examples. This is how easy it is to draw a Schrödinger cat in QuTiP. And this is a way in which it is very simple to define a quantum circuit. So this is kind of similar to many other quantum circuit libraries that are out there. QuTiP, it's really, in my opinion, one of the best getaways if you're not really familiar with quantum information and quantum computing and quantum mechanics to become more proficient with it. It has over 60 tutorials and 20 quantum mechanics lectures. Mainly the lectures were made by Rob Johansson, and the notebooks are really contributed by the very wide community. So I'm happy that, I hope that Simon is still connected. It was amazing for me last year at EuroSciPy to find out that another presenter at this conference for Python was actually showcasing how you can grasp an intuition of what does it mean to speak about quantum spins instead of classical spins. So this tutorial is now on the qtip.org/tutorial page. So as a project, things that happened in the past few years with QuTiP is that it has been supported by NonFocus, which is a non-profit open source foundation. It joined Google Summer of Code, which is a program run by Google, through which open source projects can benefit from the paid work of students that are remotely mentored. And then we have really reached out to the SciDev community, which is really taking up space. So here I'm showing some examples, goes from PyData to FOSDEM, and I really want to acknowledge the folks at the Quantum Open Source Foundation that helped start the quantum computing track there a couple of years ago. We also had held the first QuTiP developer workshop, and unfortunately we cannot attend EuroSciPy because it's being cancelled next year. And also I would like to mention the fact that QuTiP, it's a bit like AstroPy, the astrophysics library in Python, for the quantum science or quantum optics community, because it's a reference to a series of other libraries that are relying on its things. And then it is also supported by Unitary Fund, more recently as affiliated project. And I will speak about this in a moment. So let me also mention that, yeah, these are some statistics that refer to the fact that QuTiP is really used on a variety of platforms all over the world. And it is also, let's say, I would not say competing, but it's out there with libraries that sometimes benefit from flagship support from corporates or private companies. So, as I mentioned, QuTiP is a bit becoming like the AstroPy of quantum, in my opinion. So I spoke about the permutation invariant quantum solver. And another example is the QuTWorld package, which is based on QuTWorld method for quantum optimal control. This has been mainly developed by Michael Gord. And here you can see some examples of this really interesting library. Another library that is a QuTiP plugin is Matsubara, which allows to describe structured path with several methods, also through the terms of Matsubara frequencies. And then there's QuTiP.noise. So it's a QuTiP.quantum information processing module. And Boxy Lee, who's now one of the lead developers, developed last year in one of the Google Summer of Code projects. And here I'm showing because some details. This is a slide by Boxy. I think it's really interesting because there's many open source quantum circuit simulators, but this quantum circuit simulation toolbox and module in specific allows you to describe and investigate at the pulse level what happens when you give instructions such those as in the bottom left, which are typical way of representing, it's called intermediate representation of quantum circuits. So what really happens at the Hamiltonian level from the point of view of a dynamical evolution of the systems, and then it takes into account all of the power of a QuTiP different solvers to simulate what happens when different types of noise affect these dynamics. So more recently, I'm really thrilled that today we had the first kickoff meetup of a new batch of a Google Summer of Code students. Siddhant will work on Boxy's development, including more noise features for the quantum information processing unit. And also it will increase the portability of this module with the very broad and lively ecosystem that is out there from CASM, which is a sort of standard to other main libraries. Jake will perform abstraction of linear algebra data structures with a quantum object, and Azad will work on machine learning capabilities for QuTiP, such as Hamiltonian learning, so making these quantum circuits auto-differentiable with some of the toolboxes that build upon NumPy features. Let me also mention that whoever did not make it to the Google Summer of Code for deadlines or constraints in resources, also the mentors are limited in time, they can provide. There is an earlier long-running remote mentorship program funded by Unitary Fund, to which not only students but also researchers can apply to. And then let me also mention that QuTiP is growing in the different directions, and we want to avoid the feature creep, which is sometimes mentioned in open source software development, which refers to the fact that it is sometimes trying to, in libraries, it's wants to put too many things inside, and it is sometimes too hard to look after all. So it may be that QuTiP will grow more, but there will be like a QuTiP core that does the basic stuff that people use for example, Lindblad master equation simulation. And then there will be more features that will make up a sort of constellation of sister or cousins, maybe quantum cousins, like the QWorld software packages. I saw that this was one, so I am also addressing the fact that there were some questions about the integration of QuTiP with Qiskit, which is one of the premier libraries for quantum circuit simulation, which also through OpenPulse allows to simulate at pulse level quantum circuits. And so we're thinking about this sort of integrations. I've also been asked how to get more knowledgeable with QuTiP. So this is a sort of ways you can interact with a project. There are the tutorials, very great way to start, especially for me. As said, if you have problems even setting up your Python environment, you can just click on that launch binder button on GitHub, and it will start an environment of its own, and then you can just go through the script interactively. The documentation, it's a huge source of information, even for quantum physics and quantum optics. And then there is a help group on Google. And of course, we are happy to contribute and give back to the open source community. And we also have a Gitter chat where we may be more responsive. And I would like to speak about the work at Unitary Fund. And before that, I would like to give kind of like a more bird's eye overview of quantum technologies. So they're not just related to quantum computing, which may have as end application, intended application, some impact on chemistry, but also communications, secure communications by default or with different means, I would like to say. Also the possibility to simulate quantum physical systems, for example, to study materials, and with the possibility to enhance the sensitivity of research instruments, which may have a variety of applications from biology to what is called metrology, which is setting up the standards of time and space. So quantum means discrete in chunks, of course. And here I'm just showing an example in which there are some tennis balls going through 2 holes. And it's just a way to depict the statistics of what happens in the double slit experiments if you perform it with massive objects. And actually what is really amazing is that over the years, not only in that seminal 1999 paper that reports the use of, I think, light to observe the, no, sorry, maybe that was sorry, the 1999 experiment was with Fullerene, but not only we are able to study photonic diffraction, but also diffraction of atomic and massive particles. And more recently, it was even possible to observe this kind of diffraction-like patterns in organic molecules. It is now even possible to perform experiments in space that showcase and highlight inherent quantum correlations. And I think that this is one of the least looked after possibilities for expansion of quantum technologies. And I think it's really exciting, both because the Python open source community is very strong there, but because there is an open hardware and open software approach in place, it is possible with the space new economy to launch CubeSats and very small satellites. And ESA, as well as NASA, have started quantum space technologies. Not to mention that for gravitational sensors, there is an upgrade for the LIGO and Virgo experiments to inject squeeze lights in the lasers that then allow to really detect these very massive objects collapse and generation of gravitational ripples across space-time. And as the LISA project will upgrade the LIGO and Virgo experiments to space, it is also possible that it will include quantum enhanced detection capabilities. And then I also mentioned the possibility to study other systems. So let me show here some examples from Moreau and group, and also maybe looking, in which you see the interaction in the lab. You see those dots are single ions, you see. And basically it's really possible to study interaction of multiple spins at different distances and show, for example, oscillations and dynamical sort of quantum criticalities in such systems. This is just an example. There is also other platforms in which this is it is possible to study this kind of spin long-range interactions. Let me just mention that in the bottom left, there are some images that show, for example, in the center with flux qubits, thousands of coupled flux qubits to a single resonator. And then there's hybrid structures in which these systems can be studied. And I just wanted to mention very briefly that, yeah, maybe this slide is a bit technical, but this sort of XYZ model with dissipation is a field of study that I'm interested into. And very recently, a paper has been accepted on Physical Review B studying this sort of phenomena. I would like to really acknowledge Adolfo Ulbrichts, Fabrizio Minganti, Franco Nori, and Michael Voiters for their work on this stuff. As I mentioned, if you're interested in quantum technologies in general, please have a look at my Quantum Tech newsletter. And now I'm running a bit late, so I will try to squeeze it a bit. But I just wanted to give a kind of like overview on quantum technologies. So here you see what it is, a superconducting circuit. And you see this ant on one of the chips in Varrof group at ETH. And this is really to give a sense of the fact that these quantum systems right now artificially can be quite microscopic. They can be quite big. And this is one of the reasons why this sort of system, superconducting circuits, became so, let's say, central to the development of quantum computing technologies. Another way to look at it, it's by adapting this plot from Devoré and Sholkov, in which they show from basically 2000 to recent years on this semi-logarithmic scale, the fact that the qubit lifetime, as well as the fidelity, which are ways of, let's say, studying the performance of these artificial superconducting circuits for quantum information processing, has been giving a steady rate of improvement, which increased tenfold roughly every 3 years. But we should not forget that other platforms can encode quantum information, such as atoms, photons, spins, as I was showing, for example, in hybrid devices, in which, for example, there is a carbon matrix, and then there are some impurities that are engineered so to have a sort of isolated quantum bits, as well as ions, which are basically excited atoms, and due to the fact that they have a charge, it is easier to trap them inside the optical tweezers or other sorts of quantum chips. So far, superconducting circuits have been really leading due to this really exploit in the past 15 years. But one should not forget that, for example, they suffer from inherent noise due to the fact that each qubit on a chip is artificial, and so it is slightly different. And so there's also other problems such as in crosstalk and the way these chips are wired. So trapped ions are another platform where, for example, the atoms are all identical. The same applies to neutral atoms. And on the other hand, for example, photonics based quantum computing, it's very interesting from the fact that flying qubits, don't weigh anything. Their mass is zero, and they're really good for telecommunication. That's the way, for example, space quantum experiments were were made. So with this slide, I just want to say that there is a lot of effort in technology transfer at spin-off level and corporate level, as well in research labs, to really try to increase the performance of all these kind of systems. And in the bottom, I'm also mentioning this sort of neuromorphic, or let's say not gate-based quantum computing possibilities. And photonics, it's a really interesting way in which, for example, an intersection with machine learning may be viable, even if it does not pertain to the to the standard way of measuring quantum advantage. And so now I come to the fact that quantum computers really rely on open source software. And here you see some articles that, as well as reviews, that really witness the fact that in order to reach the broadest possible community of users and developers, this has been the means through which basically all of the corporates and many of the startups involved in quantum computing use open source software tools. And here I just want to highlight the predominance of Python, at least as a front-end language for many of these providers. And here I'm just showing that in some cases, it is already possible for basically anyone to access this quantum hardware from the cloud. So this is something very different from what one can do with QuTiP, because in that case, you're simulating everything on your laptop, on your PC, or on a supercomputer. In this case, there is really an interaction with some actuators in a lab. And I find this very exciting, also from the point of view of open hardware. And I really think that this is a model that should be pursued also in national labs and academia beyond corporates, because it can really be aligned with the efforts of a scientific community, a modern scientific community. And actually very recently at QTech, at Delft Polytechnique, they put online basically their quantum experiments, and they're the first provider to allow access to both a special superconducting circuit hardware, this Starmon 5 connectivity, which is a modified transmon from experts, but also to another kind of super quantum computer, which is a spin-based quantum computer of in silicon with quantum dots. And so now we have these quantum computers, and this is a slide highlighting the fact that in the past few years, this landscape has become richer and richer with a lot of projects spanning from quantum science, quantum information processing to quantum physics. And this is just a collection of some of these projects, and there are many more collected and sometimes supported by the Quantum Open Source Foundation, which I advise you to look up to. One of such projects is Xanadu's Penny Lane, which is particularly interesting because it allows to really take advantage of machine learning advances to study and characterize and investigate quantum information processing and quantum computing, and it has a lot of tutorials that are really interesting. So in the past few minutes, I just want to mention in this personal trajectory, I went from doing my research using some open source software to becoming a maintainer, and now I'm even more deeply involved with really the issues and benefits that can come from this community and can occur in this community. So open source, it's becoming really one of the main ways in which we really use and distribute software. And one of the reasons is really because the community is huge. This is really given by the fact that there is a fast adoption of this framework in machine learning, which gives a lot of advantages, and it's pursued in research, but also in industry. And also by the fact that by using open source software, one becomes a better developer, even if that's not your main job. And so this is just an example of how corporates are really getting into open source because they see the value of the community. Microsoft recently acquired GitHub, IBM, Red Hat, and both Google and Facebook have their flagship open source project that they support for machine learning. One of the languages that it's most successful in this context, it's Python, which has seen a steady growth. And I really see three reasons why this has happened. First, because it supports an inclusive and really accessible and easygoing community at different levels, from PyCons, which are kind of like gigantic conferences, to more to smaller workshops that have a more grassroots feeling, like EuroSciPy or SciPys. And then you have these sprints where people really busy. It's kind of like hackathons where people get together and try to get things together in a couple of hours. Then there is this intrinsic modularity of a language that allows different software packages, especially in science, this is useful to interact together. And then there is all these tools that really are useful for research and education. And Jupyter is the way interactive Python has evolved, really taking some of the ideas that were pioneered in Mathematica notebooks and in MATLAB notebooks. Basically, the idea that you can have interactive parts of code, but then upgrading it, for example, introducing also LaTeX, which is also open source, so you can intersperse commentary blocks with, in Markdown with LaTeX equations, as well as code blocks. And this is really useful for physicists. And so open source is really a way in which open science can be supported. Open science is really aims at removing any barrier with regards to the access to knowledge, but also to the production of knowledge through research. And one of the ways open source, I think it's really important, it's through reproducibility of results. And this is something that it's part of also of a scientific discourse right now, because with these integrated pipelines that are also rely on the cloud, it is possible to make code, tools, and data sets accessible. And not only one is able to reproduce a given on a given data set, a given set type of analysis, but also to generalize it to different data sets, applying the different techniques. And I just want to mention two things that are not related to quantum technologies, but I think it's really interesting the fact that this is seeing a fast adoption in science, for example, during this COVID-19 crisis. On the left, I'm showing what is a machine-ready, machine-learnable, ready data set by the Italian government, by the civil protection. And on the right, you see a tool, NextStrain, that allows epidemiologists to really study the different strains of this virus as well as other viruses. And so some of the tools that are important for open source development are, again, as I mentioned, Jupyter and this family of notebooks that really rely on distributed orchestration through tools such as Kubernetes and Docker, and also through the backing of Google Cloud. Google has its own collaborative method to allow people work on the same notebook, which is Google Colab. So people can change the same notebook. Whereas in other way, it is possible to really create a persistent environment of specific repositories that can be loaded and libraries that can be loaded in a given notebook. So this has gone as far as allowing some to say that the scientific paper is obsolete right now. I will not go so far, but I think that these tools are really useful for science and research right now. So this is a personal project called QuTiP project. You can check it out at github.com/Nathan Shammah. And I really would like this project to become more collaborative. So I saw some questions with this regard. And let me just mention that there are 3 basic stages in software development in open source, which are code and testing, documentation, and distribution and publications. And these tools that you see sketched here are really helping anyone, any scientist, do this in a very robust way and in a very simple way. So don't be scared that this is kind of like hands-on cookbook to try to release your own open source science library. Would I like also to mention that there are strong arguments against open source, and one should be aware of some of the threats. Of course, in research, especially if someone is developing a technology, it may make sense to have a competitive advantage. As a researcher, one may not be interested in it. Right now, it falls outside of the scope of research usually to develop this kind of open source libraries. Then if one develops a library, it will always be prone to systematic errors if others use it. And so someone needs to be aware of it as a user as well as a developer. And then of course, it's really time consuming. It's really unimaginable if you're not a maintainer to see how really maybe software developers are more used to this. Days go out with, just trying to fix a bug on some feature that you don't know. But the cool thing of code is that then it works and then it is immediate. So there's really like some focus on how open source software, it's hard to maintain for scientists. And this is at the center of an intense debate. And right now, I think that academic institutions, standard academic institutions, are responding a bit slowly with regards to what I think is really a necessity to really support this kind of open source endeavor. It's really fundamental for modern science. And for this, I'm really happy that I joined the Unitary Fund, which with regard to quantum science, it's one of the places where these sort of endeavors are really supported in a very informal and I think effective way. So let me really share some details about this. At Unitary Fund, we basically do 2 things, which is one, it's community projects, and the other one, it's in-house research. So with regards to community projects, there's a micro-grant program, which is really no strings attached, and you can really apply. You can check on unitary.fund in 5 minutes, which is just the time you need to record the video and fill out a very simple form. And this, I think it's a very effective bottom-up way to support the community, and it was really pioneered by Will Zeng, who founded Unitary Fund 2 years ago. Then we are now even supporting affiliated projects. So if you're a developer of a kind of like broader, not just at the inception level, quantum science open source library, you can consider that, and please get in touch. We give several sorts of support from expert legal counsel to help in governance, as well in funding or matchmaking with interested students or researchers. And for example, for QuTiP, Unitary Fund is providing this all year long remote mentorship project. And then we also perform in-house research. This is what is called Unitary Labs in the Unitary Fund structure. I'm really thrilled by the kind of work we're doing on error mitigation with Will, Andrea Mari, and Ryan LaRose, as well as several other folks that are researchers in the same Department of Energy grant that we work on, as well as other collaborators. And this research is also funded by IBM Research. So here, I just wanted to give you a glimpse of typical micro-grant projects. The most recent one that has been awarded is to Vincent Russo to develop the theory of quantum information toolkit, TOQITO, which has some overlaps with QuTiP, but I think it really, so first of all, it's important to develop different tools that also sometimes do the same thing, because these enhance reproducibility. And the second thing is that it really takes a modern and I've never seen this anywhere else look at games as well as gamification. So you know that Bell inequalities, or some of you may know that all of this quantum technology business basically started when a professor, John Bell, understood that the Gedanken experiment by Einstein, Podolsky, and Rosen had very specific outcomes in the way we look at quantum or non-quantum theories or other kinds of theories that are completely coherent within themselves or not. And so there are different kinds of, let's say, Bell inequality games or other sorts of generalized games that can be played. And TOQITO really allows you to try out and generalize and play these kind of games that also have a really important value for research as well as education. So this was another question that was brought forth in the questions. Please check out this library. There's over 15 projects that have been supported by micro grants. Some were already existing, some really were at the pre-seed level, we would say, for startups. Actually, one of them became a startup, which is the Quantum Programming Studio, which actually it's basically the leading product of Quantastica. Really allows to play in a native way on the web with different libraries and frameworks. Another one is by now teammate at Unitary Fund, Ryan LaRose and other co-workers of his at MISC AI, which really allows to do machine learning with near-term quantum processors. Another project that I want to highlight, but just among the many others that are amazing, I just cannot list all of 15, it's really PyZX, which really takes ZX calculus and graph representation and puts it together with quantum circuits in a way that you see sketched on the bottom. So on your left, you see this sort of standard intermediate representation of quantum circuits. And then you see that this becomes more similar to a graph. Also, to me, looks like also a neural network. And then on the right, thanks also again to the application of these PyZX methods and functions, it is possible to re-put it in shape of what looks more like a quantum circuit, but also with this information on the graph structure. And with all this, I apologize for being running a bit late, but I thank you all for your attention. And please check out more developments on Unitary Fund website or my personal website.
Thank you very much, Nathan. And now we are open for questions, both in the chat, and I would also ask some questions that were already posed earlier. And so actually, I really like your presentation. It was really nice and inspiring. And actually, two students of mine are using QuTiP, so I think, and they were all of great opinion of that. And Unitary Fund, I completely like their strategy. So it was very nice to listen. And actually, since there are so many young people now here and listening to you, I like researchers and people in universities, I actually would like to ask you two career-related and maybe personal and scientific questions. So you mentioned that actually you came in closer contact with QuTiP when you went from Italy to Japan to Franco Norris group. So, I mean, that's a big decision. And I would like to ask what motivated you to do that? And the second question is, you can answer it in the same time, is that I'm sure you got a lot of offer from academia and industry, and what made you choose this particular Unitary Fund that you are joining now? So it's also like question that I was very interested from personal and scientific point of view.
Yes, thanks. So yeah, I really moved to Japan due to the fact that Franco Nori's group was there. I mean, I love Japan. I'm even more in love with it now, but it was really like a work-based decision. I was an intern there, and I really loved the group, the way Franco manages the group, and also the fact that this is really, it's a group, but it's almost like a hub for research where there's like recurrent visitors. It's a national lab, so you're not so much stressed with teaching, although I love teaching, but actually maybe I would not have been able to have an impact on broader education through software if I were not at this national lab, because sometimes you may know it's sometimes the heavy load on teaching classes, especially in the US, I also would say can be really hard to sustain. And with regards to Unitary Fund, I'm really happy and excited about how the open source scientific ecosystem is developing. I think there is something special happening in quantum science, starting from quantum computers. I really see this idea of quantum computers connected to the cloud as a more general way through which labs are connected to the cloud, also to do experiments. It's also happening in chemistry, also in biological sciences, and but in physics, due to the fact that we really are more used to using numerical libraries because we do calculations. This is really supported by the Python ecosystem and by the open source ecosystem from start to end. I mean, at the actuator level, it might not be there yet. I think it's something interesting. And at Unitary Fund, we're really supporting, I mean, I think it was an amazing project and idea started by Will Zhang that saw a lot of support in industry, in quantum science, startups, research institutions. They see kind of like a bottleneck in the kind of like workforce that can work on quantum software, but at the same time, a lot of interest. And then I really like this idea that right now, I mean, you know it, in academia, one of the worst things is that you spend so much time writing grants and then there's so many strings attached. And some sorts of research development are really not supported right now, and they need to be, you know, fast, responsive, no strings attached. So the micro grant, it's a really, in my opinion, an amazing way to reach out to students all over the world. And I think it really increases diversity and inclusion, because I really see it with QuTiP, open source software. Sometimes it's the only way to go. If you cannot afford a license or to find the correct version of a given software, you also have to be careful with that. And the other thing I see that now this is growing in scope and in action. So we're now having in-house research, because research group really see an added value in being able to use a library that as the one we're developing for error mitigation right now, only internally, but then to be open source, using the modern standard tools of open source development, such as testing, documentations, continuous integration, and so on. And the final thing I want to say is that really it's important to support projects such as QuTiP for education and research, but there are others out there. And right now, I think things are changing in the academic funding ecosystem and policy ecosystem. But for example, it was news of last year that NumPy lost a grant from NSF, which is one of the leading US funding agencies, because I mean, it was not providing any new software as a way to support their grant and to use the grant money. And I think this is crazy, because I mean, NumPy, numerical Python, it's one of the core libraries that is used by many projects, not only in academia. I mean, even Bloomberg or the financial markets really rely on this stack, which is sometimes called the open core stack, because the basis is open source and then it becomes proprietary, which is fair it's fine, but we need to find ways to give back intrinsically to the open source software ecosystem. So if you're interested, or if you have an opportunity to pitch in your institution or company, please mention Unitary Fund. And we're starting a variety of activities. And I saw this also in the questions. We are a non-profit. It is a non-profit registered in the US. It's a 501c3, so it's charitable. And donations are the tax deductible. So I did a bit of a spot to try to get funding, but I really think it's important to science. And I mean, I was showing in the slides, there are other activities in this direction. NumFocus is supporting, in general, open source in science, very bit focused on PyData activities. I think they will be a bit disrupted by this COVID-19 crisis. But we're doing a great job. Then there is this gig economy model with open teams, which is kind of like a platform where you can become a developer that is recognized by the community, and the community can give back to you. And so I look forward to ways to foster this kind of development, and I think it will become more and more important in science.
I completely agree. Thank you very much for this very nice and extensive answer to the question. I think we understand more than why you chose Unitary Fund. So let me also then share the questions, which actually most of them you already almost answered during the talk, but let's go through which we got before your talk, and then we go to the questions that are posted now on the chat. So I share my screen. Okay, so I hope you all see it. I can make it bigger, a little bit bigger. So Sebastian from Orsay, well, asked the questions you basically answered, but maybe you can say a few words how he can contribute to QuTiP or quantum open source.
Yeah.
What would be the easiest way? I mean, you of course mentioned this, but what would you recommend it to him?
So, so for QuTiP, go on the QTIP.org website and check out the tutorials and the documentation. And there you can really find something at your level. For quantum open source, check out Unitary Fund website. There is a list of funded projects. And as I said, I just showed 4 of them, but they're super interesting. And a way to contribute is really get knowledgeable with Git and how GitHub or GitLab works. And that's the basic. You can also check Quantum Open Source Foundation and go there. Yes, so that's my answer.
It was okay. And Leah from the University of California, Santa Barbara asked that what are the best practices for companies, software engineers, and the public to support and advocate for open source quantum software and quantum education? Well, one of a large part of your talks were about that, but perhaps you could summarize 1-2 sentences. This, I mean, she also wrote, "Samurai will be open sourcing."
Yeah, this is fantastic, and I would like to get in touch with Leah. Yeah, so
we will get you.
So I mean, the Quantum Open Source Foundation has a list of supported projects. I want to say that this is something I think that there is a lot of space for Unitary Fund to do, and I want to mention that the QuTiP textbook by basically Abe Asfaw and collaborators. It's a very interesting tool, and we're looking forward with like further discussions in the QuTiP forum to there are several courses teaching from quantum machine learning to quantum optics using QuTiP from France to the US to other places. And so we would like to create some space for professors to put this material, to showcase it, and also to learn from others. And let me just mention that a very interesting way to do this, it's with Jupyter Notebooks, of course. But if you want also to think it as a cohesive way, as a textbook, it's also, or as notes, it is also very nice to do it with a Jupyter book, which is a kind of like evolution of a Jupyter notebook, putting together the HTML features as well as others of encoding.
Perfect, I think. And we will, of course, ask her whether we can somehow get in contact with you, but this would be, I think, very interesting. So Manoj from India asked basically, I mean, QuizKit, of course, helps to interact with IBM quantum computers, and QuTiP can simulate a lot of quantum physics. Is there a way you could somehow mix the codes? I mean, as it was suggested here.
So let me mention that we're working on it, not only with QuizKit but with other also other providers, and not only in corporate research but also in academia. So there's different directions this can take. Again, one of the questions is this feature creep. QuTiP should not do too much, and as any library should not do too much, because when you stretch it too much, it's like pizza dough. If you stretch it too much, then you start having holes. And basically, to make it as maintainable as possible, I do envision, I mean, this is something I proposed and came up also recently with speaking with some startups and other several corporates. It's really to try to have something like a QuTiP lab, QuTiP labs, and then you can give pulse level control. But please check out the results of Google Summer of Code projects, because we may have more into this direction, especially given the recent feature by QuTiP creator Paul Nation and collaborators in QuizKit, which is OpenPulse, which I think could really integrate well with QuTiP. Let me just mention that one interest, it's of course you would like to run this on hardware, but the cool thing, one of the coolest things that has been created by Box's noise module for quantum secrets, it's that you can create your own processors. So basically, it's a very intuitive way in which you can set up a device and its connectivity, and as well some rules to merge gates or have some native operations. And so basically, this is also something to consider for research.
Perfect. I really liked it. So did I understand well that in the QuizKit Pulse, QPulse program, many of the people who work for QuTiP also work there, or you can, or that I misunderstood maybe.
You said the QPulse.
In the QPulse, yes. Or you can just, you say that it's that the Q.
No, sorry, because I mentioned, did I mention Q? So maybe it was a lapse. So I mentioned OpenPulse, but QPulse. Yeah, but actually QPulse, it's actually an existing package, and it's also trying to integrate with QuTiP. So QPulse is a package developed in Germany at Aachen Technology University in Hendrik Bloom's group, and basically this allows to have interaction and control, and also optimal control with quantum spins. And so we're also thinking of integrating with that. There is many possibilities. I mean, I just saw a talk by Loïc from Pascal, which is this spin-off in France that allows access to Rydberg atoms, and they also allow Hamiltonian access to their system. And I think this is also something that is really exciting to do research for spin models that could have an integration with QuTiP.
Thank you. Then Jean-Daniel asked a question that you touched upon, although you didn't give an answer. So maybe we can get maybe some answers from you now, or what you think. So he says that modern research greatly benefits from computational tools, which we all agree on.
Yeah.
But,
so yes, I would say,
what is a just way to reward it, and scientists who do the code? So what would you say for this?
So yeah, no, this is a very nice question. So let me answer in a bit an articulate way. And so there's different ways. First of all, I agree. I mean, someone said that software maintainers are these unsung heroes of modern science.
Absolutely.
I don't know it, but I know that it's a lot of pain, and sometimes it's really just out of pure passion, because otherwise you don't get out of fixing the bugs. So this is true. One thing is that up until recently, it was possible for folks to be at national labs, research institutions, and devote some time to open source. It depends, or even in corporates. Some corporates are making this more easy. Some settings are making it harder because of licenses and so on, and time that is used not for the main focus. So I think if you're head of a group and so on, even in research, in academia, please allow this to happen. The second thing, it's publications, because the metrics,
Exactly.
the special money of academia is right now, there is this hysteria around the H-index, metrics, Google Scholar, and so on, but that's true. And that's a way also to evaluate the impact of a project. So this is happening more and more. There are more and more journals, and actually my project, Scikit project, you see a list of them. They go from Software X to computer physics communications to Quantum, the journal, to Cypos Physics, to even the Journal of Open Source Science. So basic open source software. Basically, there are several ways for which you can publicate. Something I did not mention explicitly, but I was showing a log of Zenodo for these open source libraries. This is very interesting, because you know that when you publish an article on the archive, it's there, but usually you cannot cite it in even in grants, because it doesn't have a specific bibliometric reference, this DOI code. And actually with Zenodo, you get immediately, even beyond peer review, if you have a given data set or software package, this DOI code. So this is another way you can make this work emerge. And what I want to say is that really Unitary Fund is not because I work there, but it's one of the ways to which, by donating, and this is all deductible because it's a charity, by donating to Unitary Fund to run its its microgrant project program or affiliated program, you can really give back to the quantum and general scientific software community.
I think that was also very nice and extensive answer. Thanks. Like I said a lot of times, exactly because I fully agreed with this actually. So Laura from the Excel Energy Group in Canada asked a question that you will like actually. She first of all praises Unitary Fund for providing terrific support for newcomers and projects, and asks then, what involvement of the wider industry would Unitary Fund welcome to support the mission of Unitary Fund in awareness, fundraising, collaboration? So if company like this company, another company would approach you, what would you say? How could they help Unitary Fund? Which way?
Yes, again, please get in touch with me, Laura, for, helping in fundraising. This is something that we're doing, and we're currently doing with these various stakeholders. And again, there are sometimes corporates, sometimes there are startups in quantum, sometimes there are journals such as PLOS as Given Back or some other sorts of organizations. And so helping spread the message would be great. And so please, we can get in touch in another setting. I'm already reading Raphael's question about compiler programs other than QuTiP I use on my daily basis, and to find better solutions of norm problems. And what do you think is the correct solution, like NP-hard? So I think that, so this question is amazing, Raphael. So I hope that you have some emails I can get back to, because actually this is something I'm working with collaborators right now. And as recently as like 2 hours ago, I got an exchange with one of my collaborators about this. And it's also something we're involved at Unitary Fund since recently, but all the Unitary Labs team is involved into this. So there is nothing I can say now but let's say that I think it's what you say. It's absolutely an issue. Both in the literature, is not really clear how many compilers are there, and this is also an impact on error mitigation techniques and the way you can benchmark them. So I can get back to Rafael privately.
Yes, we will. If it's okay, we will contact you. So we will put you in contact. So Gail from the Weizmann Institute asked a question that we are very fond of with Abu, and I personally, because I teach actually quantum information processing at the same time as quantum mechanics and using different software like QuTiP. So the question is, do you feel computationally based teaching of quantum computing should come in as early as possible in the teaching curriculum of quantum mechanics? Do they work well on the first course in quantum mechanics? I mean, be careful what you answer in QWorld session.
Yeah, no, I think it does. And look, I mean, one of my dreams is actually a quantum optics course that really runs partly with the hardware in the back end that students can access to live if they want, as well as the simulation. And I must say, we must give credit to the QuTiP community team, Abbas Fawa, as mentioned, but many others that are really making, at least for the quantum computing side, this is really easy to do with QuTiP.
Yes.
We're also integrating Open Pulse to show this pulse level control such that you can really see the evolution of it. This is now, I think, I don't know if it is accessible to all, and it's now only with a limited chip, maybe just 1 qubit or 2 qubits, but I think it will grow, maybe with some partner associations. I think that this is something that can grow, again, maybe with QuTiP, maybe with other options, in a more really crowdsourced way, in a way that, a lab puts its experiment online. It's kind of like what I call the Uberization of quantum computing, but also quantum experiment time. So of course, there is a lot of strain, a lot of efforts in APIs, actuators, and standardization of tools. So, I mean, it's no wonder that to make these really robust and systematic and general, this can take millions. But I think it does fit well in the mission of national labs, US national labs, European national labs, CNR in Italy, CNRS in France, Max Planck Institute, and so on. And so I really see a future for this in the next years. And again, as I mentioned before, Jupyter Book, it's one of the tools, as well as My Binder, which is cloud-based Jupyter notebooks, to allow students to play with this framework without, especially if it's the first course in quantum mechanics, without getting stressed with all the information about how to set up open source software development environments. And I would even get this to another level, Gallo question, which is, I think that modern computing programming in universities will need to be paired or reframed in the framework of open source software development. In that way, it may be, I mean, you need the basics of numerical computing and programming, but I think that now it's important to have maybe elective courses, but on open source software development.
Yes, I fully agree. So I think also this is one way of going. So the last question from the questions that were posted previously, before your talk, is from David USA, who asks how to start learning QuTiP. What would be the tips and what would be the way?
Yes, as I mentioned, check out qtip.org/tutorials. I think that's the best source of information.
Perfect. And now we got a few questions during the webinar. A question from Shubham. So would you share some references where QuTiP is used for material simulation? I mean,
yeah, I mean, this is I'm sorry, but it's so on the QuTiP website, there is a section that is not up to date, but contains a lot of information about research works and notebooks that use QuTiP for research and papers. Then if you go on Google Scholar, which is this bibliometric tool through which you can check which papers cite which others, and you just search QuTiP, you will see that there's the 2 QuTiP papers, and they have overall over 1,000 citations. So you can really check there. And I would say that in general for materials simulations, this is done in connection to quantum optics frameworks, such as noisy XYZ model, can really also describe basic material science playgrounds or like basic problems. So with this regard, I would tell you to check out the XYZ paper that we just got accepted in Physical Review B, for example.
That you mentioned. Yes,
yeah.
Perfect answer. So Peter had a very interesting question. When would you use QuTiP over, for example, Qiskit as a quantum computing framework? In which situations?
So what does it mean when I should use QuTiP over? So,
I guess
so Qiskit, yeah. So okay, understood now. Sorry. So basically, let me just say that QuTiP is very good at describing noise and dissipation in quantum physics systems. And so every time you're interested into describing this kind of noise, I think that's the way, one of the ways to go. I mean, there's other tools. I was even showing them in the slides, maybe I were not mentioning. There's a quantum optics toolbox in Julia, there are other specific toolboxes. Now, I mean, most of these quantum circuits toolboxes have density matrix level or noise level simulation. But really, QuTiP as a variety of dynamical solvers, there is a match. So it is clear that if you're just, if your researcher interest is just informed with an intermediate representation level of quantum circuits, maybe other libraries are more developed, certainly. I mean, from Qiskit to Circ to other things. But if you want to find integration with a quantum optics framework of trying to characterize these dynamics, I think QuTiP is the way to go.
Okay. This is clear actually. So Karim, actually, who is one of those 2 students who praised actually QuTiP for me, asked the following question: how different is the noise simulation in QuTiP from Ignis module in Qiskit? Well, that's more readout error, but that's a fair question. So
yeah, so actually I would say that Qiskit.air is maybe as some features that are similar to what, and also OpenPulse as some features that are similar to what has been developed in QuTiP.QIP noise module by Boxy. So let me just mention that the circuit module in QuTiP, it's not the main module, and it integrates with other noise modules. And at the center of QuTiP, it's basically, as it happens in Python, it's this quantum object, which is a class that gives you information about whether you're dealing with a Hamiltonian, you're dealing with a super operator object, and so on. And this kind of information, it's really useful to then do some noise simulation, even beyond quantum circuits. Ignis, my understanding, I'm not super familiar. It's more, as you said, for stuff like randomized benchmarking. It's more really for characterizing the noise that occurs in a given Qiskit device or ideal device. Whereas the Qiskit Air does have some noise models that kind of overlap with the QuTiP.QIP noise features.
Okay, thanks. And also Karim asked a following question. I mean, there is a background that there is like a growing quantum community in Egypt, and actually they are doing many meetups, and they will actually join soon QWorld as QEgypt as a Q cousin. So he asked that in this summer in Egypt there will be some quantum meetups. like the one that happened last year, and here is the website. How can I, as a member, get the Unitary Fund involved in such a meetup event?
Yeah, so yeah, please reach out. I mean, this sounds super interesting, and please, I mean, maybe I can get in touch with Karim, or please
Sure.
send me an email at nathan@unitary.fund. And in general, these sort of decisions are taken by a board at Unitary Fund, so it's not something I can say yes alone, but I think it would be very interesting to talk this out.
Yes. Okay, Adam, who is already like a very prominent member of QWorld, actually, Poland in particular, he and also likes Julia very much as a programming language, as the following question: is there a chance, or does it even make sense, to copy functionality of QuTiP into Julia?
Yes, so actually, as I was kind of mentioning, I was showing in the slides, there is a quantumoptics.jl library, and it does not have all of the functionalities of QuTiP. But of course, I mean, you know, or maybe some don't know, but Julia is a language that was born out of MIT, and specifically for scientific coding, different to Python, even if Python now is so popular. And it gives a lot of transparency to low-level access of what's happening in the machine. This makes things optimized. We all know that Python as an interpreted language is inherently slow, but one of the reasons why it's so popular, it's due to this really modular approach, and the fact that it can also interface with libraries such as Cython, or now just-in-time compilation, Numba, and so on. And so actually it tries to compensate these these hiccups. But I mean, there are functionalities in QuTiP that have moved into Julia through thanks to the quantumoptics.jl project that revolved around the Quantum Optics Institute in Innsbruck, ICOCI. I think personally that this space will grow further. So there is a lot of activity in Julia, also in Quantum. One of examples, it's yao.jl, yao.jl, which is a way to benchmark and play with differentiable quantum series representations. At the same time, I must say that I may be biased.
In Waterloo, right? That is developed in Waterloo and in China, maybe.
Yes, but I think that it's the Julia ecosystem is not as robust as the Python ecosystem at this point, which doesn't mean that one should not go there. I just think that the maintainability of Python projects, maybe in scientific ecosystem, maybe it's easier.
Thank you very much. I mean, I agree that maybe it's not so robust, but that ecosystem is actually much smaller, but they are really attached to Julia. I have a feeling about this. So Marcos asks, what is the minimum background on quantum information and I guess quantum physics to start using QuTiP?
Yes, so...
and this is that's Karim, yes. Yes, please.
So, yeah, I mean, just different people and they have different answers. My take is that QuTiP allows you to understand quantum optics, and actually just by reading the documentation from start to end, you understand a lot of quantum optics, and actually from a different perspective, even if you're an experienced researcher. And the reason why, it's like, let's take the example of this dynamical equation that allows to describe noise, which is one case with very simple approximations, such as there is a memoryless environment and so on, gives you this Lindblad mass equation. For a lot of time, people have thought of this in terms of linear functional, that maps certain objects into other certain objects, Hilbert spaces into Hilbert spaces. But actually, when you write it in QuTiP, as well as with other software, for example, but in QuTiP it's very easy to do so, to write this object is called a Liouvillean. Since it's a linear functional, it is represented by a matrix. And as a matrix, has a lot of properties. So right now there's a lot of efforts in studying, for example, the spectra of such matrices, these Liouvillean spectra. And of course, it has an analytical input. But I think that part of the reason why this is so popular is because people recognize that these are matrices. And so you study the properties of number-based matrices. And so it really gives you a different perspective on the way you sometimes picture quantum optics and quantum information. So, I mean, you don't need much to start using QuTiP. I still think that the information asymmetry between experts and non-experts, it's quite high in quantum. And it is due to the fact that you need to have some sort of scientific background or inclination. And so right now there's a lot of ways to get involved into this. I still think that if you have the opportunity, I don't know if Marcos is a student or not, taking a course with the aid of a professor, it's one of the best way to get proficient in that. But now there is, you know, online courses, MOOCs, and so on. And so you can become more, he's a professor in Paraguay. Okay.
Okay. And Karim, who already asked a question, or two actually, asked the following question. Maybe the answer will be very easy again, in the sense that it's you. So he is working as an AI engineer, and he's thinking of contributing to the JAX project. How could he do it?
Yeah, so I'm not familiar with the JAX project, but in general, you should. I mean, we can do it right now. We can Google JAX. So I don't know. Maybe if he was mentioning the JAX integration in QuTiP, what I can tell you is please get back to me, because we have a student that is working. We work on it during the summer, but he's interested in JAX in general. This is, you can find it under Google's GitHub account. And basically, I mean, you see there is the GitHub project and it has issues. So one of the best ways to help a project, open source project, is to start solving their issues. And sometimes they have some other sorts of ways that you can interact. For example, in QuTiP, we have this Google's forum or Gitter. Some other projects have discourse-based. The app is called Discourse, where you can interact with developers. But yeah, just check out the GitHub repository, and you will find ways to contribute.
Okay, I mean, also is interested in combining, so I guess he just contacts you, right?
Yeah.
Yeah. So finally, a question for me, because I and Maxims and Pavel, who both also are here, we are we are responsible for integrating different countries into QWorld. And Peter is asking, is there a QWorld UK branch? If not, how could I start? So basically, there is one is being established in Ireland, but not in the UK. So actually, you should just email me, and I gave my email, Zimboras@Sultan being appointed. And so, thank you very much. Thank you very much, Nathan. It was an excellent talk, and you gave great answers and very inspiring answers. And the talk was also that. Thank you again for being.
Yes.
Yes.
Yeah, I would like to thank everyone who's still connected. I'm sorry I cannot say hi, but in person. And yes, again, check out unitary.fund for updates, and my website, nathanshammah.com, if you're interested into a newsletter or some of the other activities I'm involved with. And thank you, Zoltan and Abu, for setting this up. I'm sorry I went over time, but I also started a bit
This was
later.
perfect.
But I really enjoy the Q&A part because I think it's very interesting.
That was
it was very good. Thank you very much. Nathan, they ask whether your presentation will be available. Will you share with us, or can you put somewhere on your website something?
Yes. So we can follow up with this, but I can even send you my PDF slides, or I can put it on my website. So either way, it's fine.
It can be public, yes?
Yes.
Then we can put a link under YouTube. This video will be on YouTube, then we can put there as well. So after Nathan, we can still informally talk about QWorld if someone is interested. I really want to thank these 20 plus people still are here and just following.
Amazing, yes.
Thank you very much. Also, thank you very much to Nathan. It was really inspiring talk, and I guess question answer session simply great.